Top 20 data science interview questions and answers. Preparing for a data science interview requires a strong grasp of statistical concepts, machine learning techniques, and practical problem-solving skills. The following top 20 data science interview questions cover critical topics such as statistical tests, model evaluation, data handling, and algorithm optimization. Designed to test both theoretical knowledge and applied expertise, these questions, each explained in approximately 70 words, provide a comprehensive guide to mastering key concepts and excelling in data science interviews. 1. What is the difference between parametric and non-parametric statistical tests? Parametric tests assume data follows a specific distribution, e.g., normal, and use parameters like mean and variance, e.g., t-test, ANOVA. Non-parametric tests make no such assumptions, using ranks or medians, e.g., Mann-Whitney-U, Kruskal-Wallis. Parametric tests are more powerful when assumptions hold. Non-parametric tests are robust for non-normal or small datasets but may have less statistical power. 2. Explain the central limit theorem, CLT, and its importance in data science. The central limit theorem states that the sampling distribution of the sample mean approximates a normal distribution as sample size increases, regardless of the population's distribution. In data science, CLT enables reliable statistical inference, hypothesis testing, and confidence intervals, even for non-normal data. It underpins many algorithms and ensures robust predictions, making it critical for analyzing large datasets and modeling uncertainty in real-world applications. 3. What is p-value and how do you interpret it? A p-value measures the probability of observing results at least as extreme as those obtained, assuming the null hypothesis is true. A smaller p-value, e.g., less than 0.05, suggests strong evidence against the null, leading to its rejection. A larger p-value indicates insufficient evidence to reject the null. Interpretation depends on the significance level, alpha, context, and study design, avoiding over-reliance on arbitrary thresholds. 4. How would you handle missing data in a dataset? Handling missing data involves identifying patterns, random or systematic, and applying techniques like 1. Deletion, removing rows/columns with missing values, if minimal, 2. Imputation, mean, median, mode, or advanced methods like KNN, regression, 3. Model-based approaches, e.g., treating missingness as a feature. The choice depends on data size, missingness proportion, and analysis goals, ensuring minimal bias and preserved statistical power. 5. What is the difference between correlation and covariance? Covariance measures how two variables change together, with positive/negative values indicating same/opposite directions, but its scale depends on variable units. Correlation, e.g. Pearson's, standardizes covariance to a range of -1 to 1, making it unitless and easier to interpret. Correlation indicates strength and direction of a linear relationship, while covariance provides raw covariability, useful in portfolio theory but less interpretable across datasets. 6. Explain the bias-variance trade-off in machine learning. The bias-variance trade-off balances model complexity. High bias, simple models, risks underfitting, missing patterns. High variance, complex models, risks overfitting, capturing noise. The goal is to minimize total error, bias plus variance, for optimal generalization. Techniques like regularization, cross-validation, or ensemble methods help. For example, a linear model may have high bias. A deep neural network may have high variance, requiring careful tuning for balance. 7. What is cross-validation and why is it important? Cross-validation assesses a model's performance by splitting data into training and validation sets multiple times, e.g., k-fold, divide into k-subsets, train on k1, validate on 1. It estimates generalization error, reducing overfitting risk. It's important for model selection, hyperparameter tuning, and ensuring robust performance on unseen data, especially in small datasets, by maximizing data use and providing reliable performance metrics like accuracy or RMSE. 8. How does a random forest work, and why might it perform better than a single decision tree? A random forest is an ensemble of decision trees, each trained on random data subsets and features, bagging plus feature randomness. It aggregates predictions, majority vote or average, to reduce overfitting and variance. It outperforms a single decision tree, which may overfit or be unstable, by improving robustness, handling complex data, and reducing error through diversity and averaging, especially for noisy or high-dimensional datasets. 9. What is regularization, L1 versus L2, and how does it prevent overfitting? Regularization adds a penalty to a model's loss function to discourage complexity. L1, lasso, adds the absolute value of coefficients, promoting sparsity, feature selection. L2, ridge, adds squared coefficients, shrinking them evenly. Both prevent overfitting by reducing model sensitivity to noise and limiting large weights. L1 is better for sparse models. L2 handles correlated features well, improving generalization on unseen data. 10. Explain the difference between supervised and unsupervised learning with examples. Supervised learning uses labeled data to predict outcomes, e.g., regression, predicting house prices, classification, spam email detection. Unsupervised learning finds patterns in unlabeled data, e.g., clustering, customer segmentation, Dimensionality reduction PCA for visualization. Supervised learning requires target labels for training, while unsupervised learning explores data structure without predefined outputs. Useful for exploratory analysis or when labels are unavailable, like anomaly detection. 11. How would you optimize a slow-running SQL query? To optimize a slow SQL query, 1. Analyze execution plans to identify bottlenecks. 2. Add indexes on frequently filtered/joined columns. 3. Avoid unnecessary columns and select. 4. Use appropriate joins and filters. 5. Partition large tables. 6. Rewrite subqueries as joins. 7. Limit result sets with where or limit. 8. Cache results for repetitive queries. Test changes and monitor performance to ensure efficiency without compromising accuracy. 12. Write a Python function to remove duplicates from a list while preserving order. Python. Copy. Def remove _ duplicates, LST. Scene equals set. Return x for x in LST if not, x in scene or scene. Add x. This function iterates through the input list, tracking scene items in a set. It preserves the original order by including only the first occurrence of each element in the output. For example, remove _ duplicates. 1, 2, 2, 3, 1, 4, returns 1, 2, 3, 4. It's efficient, and handles any hashable elements. 13. What is the difference between inner join, left join, and right join in SQL? Inner join returns rows where matching values exist in both tables. Left join returns all rows from the left table, with matching rows from the right, nulls if no match. Right join returns all rows from the right table, with matching rows from the left, nulls if no match. Inner join is strict. Left/right joins preserve one table's data, useful for incomplete matches. 14. How would you handle imbalanced datasets in a classification problem? For imbalanced datasets, 1. Resample data, oversample minority with SMOTE, undersample majority. 2. Use class weights in models to penalize misclassifying minority. 3. Choose metrics like F1, score or AUC over accuracy. 4. Apply ensemble methods, e.g., random forest, robust to imbalance. 5. Collect more data if possible. Evaluate trade-offs to avoid overfitting or bias, ensuring the model generalizes well to minority classes. 15. Explain the difference between list comprehension and a generator in Python. List comprehension creates a full list in memory, e.g., x *** 2 for x in range 10. Suitable for small datasets but memory intensive. A generator, e.g., x *** 2 for x in range 10. Produces values lazily, one at a time, saving memory for large datasets. Generators are iterated once and cannot be reused, while list comprehensions allow random access. Use generators for memory efficiency, lists for repeated access. 16. How would you evaluate the success of a recommendation system? Evaluate a recommendation system using 1. Accuracy metrics, precision, recall, F1, score for top-end recommendations. 2. Ranking metrics, NDCG, MAP. 3. User engagement, click-through rate, conversion rate. 4. Coverage, diversity of recommendations. 5. A/B testing for real-world impact. Offline evaluation uses historical data. Online tests measure user behavior. Combine metrics to balance relevance, diversity, and business goals, ensuring alignment with user satisfaction and objectives. 17. If a model performs well on training data but poorly on test data, what could be the issue, and how would you fix it? The issue is likely overfitting where the model learns training data noise. Fixes include 1. Simplify the model, reduce complexity. 2. Apply regularization, L1/L2. 3. Use cross-validation to tune hyperparameters. 4. Collect more diverse data. 5. Apply dropout in neural networks. 6. Use ensemble methods. Evaluate with validation sets and monitor generalization to ensure robust performance on unseen test data. 18. How would you approach feature selection for a high-dimensional dataset? 4 high-dimensional datasets. 1. Use filter methods, e.g., correlation, mutual information, to rank features. 2. Apply wrapper methods, e.g., recursive feature elimination, for model-based selection. 3. Use embedded methods, e.g., L1 regularization, to penalize irrelevant features. 4. Remove redundant features via PCA or variance thresholding. 5. Test subsets with cross-validation. Balance interpretability, model performance, and computational cost, prioritizing features with strong predictive power. 19. Explain how you would design an A/B test to measure the impact of a new feature. To design an A/B test, 1. Define the hypothesis, e.g., new feature increases engagement. 2. Select a metric, e.g., click-through rate. 3. Randomly split users into control, old feature, and treatment, new feature groups. 4. Ensure sufficient sample size for statistical power. 5. Run the test, controlling for external factors. 6. Analyze results using statistical tests, e.g., T-test. 7. Validate findings and implement if significant. 20. You have a dataset with millions of rows but only 100 are labeled. How would you build a model? Use semi-supervised learning. 1. Train a model on the 100 labeled samples. 2. Predict labels for unlabeled data, pseudo-labeling. 3. Retrain with combined labeled and pseudo-labeled data. 4. Use active learning to prioritize labeling high-uncertainty samples. 5. Apply transfer learning with pre-trained models. 6. Use clustering to identify patterns in unlabeled data. Validate with cross-validation, ensuring robustness despite limited labels, and iterate to improve accuracy. Mastering these top 20 data science interview questions equips you with a robust foundation in statistics, machine learning, and data handling techniques. From understanding the central limit theorem to optimizing SQL queries and tackling imbalanced datasets, these concepts are pivotal for success in data science roles. By studying these concise yet comprehensive answers, you'll be well prepared to demonstrate your expertise, problem-solving skills, and ability to apply theoretical knowledge to real-world challenges in any data science interview.